Hello, my name is Roshni Purohit, and this is Physics 2211, Lab 01, Constant Velocity. First, let's go over a brief overview of what I'll be covering here. First, I'll start with an introduction to Lab 01 and the concepts covered, the tracker analysis, my computational model, a comparison between these two, and further questions that are important to analyze. Let's start by introducing the key concepts that will be very relevant to this lab. First, let me discuss what constant velocity is and how it pertains to Newton's first law. Constant velocity occurs when the sum of net forces is zero. This also means that there is a constant position over time. When examining Newton's first law of inertia, we can see that it states that an object remains in motion or at rest at a constant speed unless acted upon by an external force. This means that if there are zero net forces, speed and velocity should remain constant throughout. For this lab, there are two essential equations that will be used in the computational model as seen below. The position update formula provides us with the final position. In this lab, since there is a constant velocity throughout, v final is equal to v initial, making the v average in this equation equal to the v initial as well. The velocity update formula provides us with the final velocity when there is a constant net force acting upon the object. In this lab, since our net force should be equal to zero, v final will be equal to v initial as well. In this lab, we're under the assumption that there is no net force, meaning there's no friction nor air resistance acting upon the marker when we roll it. Additionally, we are focusing on just the x-axis movement and disregarding movement in the y and z axes. Since friction and air resistance are ignored, this means that there is zero net force acting upon the marker when it is in the process of rolling. After providing an initial force to get the marker rolling, when the marker is in the process of rolling, the force due to gravity and the normal force should cancel each other out as demonstrated in these images. This means that there's no net force and that velocity will be constant. Additionally, the systems in this is the marker and the surrounding are the environment, which includes the table, air, and more. Now, let me talk about the purpose of this. The purpose is to measure the motion of an object, in my case an expo marker, while it is at a constant velocity. I should expect to see a constant position over time. I will then compare my observations to the computational model, which is a prediction of what should be observed. Now here is my tracker analysis of the motion of the expo marker rolling along a table. In this, I was able to measure the position of the marker in relation to the time. I chose to orient my origin at the center of the marker and made it so that the marker rolls in the positive x direction from right to left. Next, I began to write pieces of code for my computational model. I used the coding equivalents for both the update velocity and position update formulas so that Newton's second law had application throughout my code in order to get an accurate prediction. These are them depicted below. These are also more snippets of my code, where I updated the mass of my object so that it can coincide with my expo marker, even though this is not necessary since mass would end up canceling out in my formulas regardless. I set my initial position to 0.012, which is obtained from my tracker data, and set my initial velocity to 0.179, which I acquired with the formula of change in position over change in time. My frames were set to 0.04, which were the size of each of my time steps. Here's more of the code where I incorporated the update position and velocity formula coding equivalents in order to get an accurate prediction. Additionally, note how net force is zero in order to account for constant velocity. Here are the results after I ran my computational model. Note how there is a constant velocity throughout. Now here's a graphical representation of my tracker analysis observed versus my computational model predicted. I acquired this by inserting all my data into Excel. The position is depicted on the y-axis and is measured in meters, and on the x-axis we have the time, which is in seconds. Now let's go over the differences and similarities between the two. Initially, the velocity between the tracker and the computational model were incredibly similar. However, towards the end, the computational model's rate overtook the tracker's and proceeded at a steeper constant rate. This means that eventually the tracker began to decrease in speed due to some net forces being present, as this is a real-life model. Some potential errors that there was there was no consideration for the y-axis and z-axis, meaning that position may be affected due to this. More so, there was likely presence of net forces such as friction, which made velocity non-constant, especially towards the end. Lastly, there may have been errors in placing the center of mass on the marker in each frame in the tracking process. Lastly, let's discuss the additional questions. What if the axes were flipped? This means that there would be a flip in the direction of the velocity and position, which would result in a negative slope instead of a positive one, as the data would be flipped along the x-axis into the negative region. However, the magnitude of neither the velocity nor the position vectors would change, as it would be squared and then square rooted. What does this mean? Is it possible to say that the forces being added together to give zero net force in the case that you observed? Well, no, it is not possible for me to say how many forces are involved into creating a net force of zero. Though we can say that both forces due to gravity and the normal force cancel out, other forces are not as easy to predict. In real life, we know that both air resistance and friction forces are going against the marker, but we cannot exactly which and to what degree other forces are acting with the marker for it to continue moving.